Hello and welcome to today's lecture on pass transistor logic circuits. In the last couple of lectures, we have discussed how Boolean functions can be realized by using static CMOS circuits and dynamic CMOS circuits. Those are essentially known as gate logic, because inputs are applied to the gate and you take the output from source or drain of the transistors. And earlier we have discussed about the use of transistors as a switch. Today we shall discuss how you can realize Boolean functions using transistors as a switch. This is typically known as pass transistor logic circuits. So, here is the agenda of today's lecture. After giving a brief introduction, I shall discuss about pass transistor logic circuit design rules, then discuss about their advantages and disadvantages, and also we shall discuss how various disadvantages can be overcome. So, let us start with a brief introduction which is essentially a recapitulation of what we have discussed earlier. We know that an ideal switch have 0 resistance, and that means whenever you apply an input it will reach unattenuated. Say suppose this is a switch, whatever is inside let us forget. So, let me represent it by this, a switch, and you are applying an input V in and you are getting an output. Ideally V in should be equal to V out when switch is on, and whenever switch is off, then V in should not be V what irrespective of V in, V out should be equal to 0 volt or 0. So, when switch is off. So, this is the ideal characteristics, as you know, and we also know that a relay, which is a electromechanical device, can act as a ideal switch, as an ideal switch. However, it is very slow. So, switching characteristics is not acceptable in present day circuits. There was a classical book, still it may not be available now, written by Caldwell, who provided a chapter where you can realize circuits using relay logic. That means, using relays as the building blocks, Boolean functions can be realized. So, relay logic is provided, and in case of relay, presence of input, that means whenever you apply, say suppose this is the relay, and if you apply an input which is equal to say high, that means if input is available, then you get, if the switch is closed, you get V, whatever is V in you get as V out. That means, V out is equal to V in irrespective of high or low. Whenever V in is not present, that means there is no input applied to it, then V out is equal to 0. That means, in case of relay logic, absence of input provides a 0 output. That means, that absence of input is treated as low input, and at the output you get 0 whenever the switch is closed. So, however, as we shall see, pass transistor logic is different from relay logic, because we cannot really use the techniques that has been used to realize Boolean functions by using relay logic to pass transistor logic, and in what way they differ we shall discuss in detail. But before that, as I told, we shall be using MOS transistors as switch. Very quickly let us recapitulate what we discussed earlier. We know that an NMOS transistor as a switch can be used, and when the gate voltage is 0, then the transistor is off, and when gate voltage is VDD, the transistor is on, and we also know that a low level signal can be passed through the switch without any degradation, as it is shown here. If 0 volt is applied, you get 0 volt, and a high level signal cannot be passed without any degradation. As we know, at the output you will get VDD minus VTN, where VTN is the threshold voltage of the NMOS transistors. So, this is the characteristics of a NMOS transistor as a switch, and similarly if we use a PMOS transistor as a switch, when VGS is equal to VDD, the transistor is off. If you apply VDD here, the transistor is off, and when VGS is equal to 0 volt, the transistor is on. And as you know, a low level signal cannot be passed without any degradation, because you will get a voltage which is equal to VTP, I mean absolute value of VTP. You apply a volt VDD here. That means, if you apply 0 volt here, you will not get 0 here, but you will get a minimum voltage of VTP, because this transistor will turn off when the voltage gets discharged beyond VTP point. Then high level signal, however, a high level signal can be passed without any degradation, as we know. So, if you apply VDD, you get VDD with a 0 in the 0 applied to the gate. So, minimum voltage that it can pass is VTP. We can make a conclusion from this, and we can combine the advantages of NMOS and PMOS transistors to realize a transmission gate, where both 0 and high level, low and high level can pass without any degradation, and where we use two transistors, one NMOS and one PMOS in parallel. However, this will require control signals. You can see complementary control signals. That means, if this is the switch, this is the transmission gate, then if you apply some say control signal, if you apply here, this is your V in, this is V out. That means, if you apply 0 here, you have to apply 1. That means, you may have to use an inverter, and if this is the control signal coming from some other source, to apply to the two gates. So, you require either complementary signals, or you have to use an inverter to complement the control signal to be applied to the other input. So, the number of transistors that you require in realizing a switch is quite large in case of transmission gate used as a switch, and that is so. We can say that we can, from this we can, our observation is MOS transistors can be used as switches with some limitations. Transmission gate provides near optimal switch. In case of transmission gate, as we have seen, two parallel transistors supply current to the load, and realization of Boolean functions using transmission gate requires larger area, because as we have seen, you not only require two transistors to realize a switch to generate control signals, you may require another inverter. So, that is the reason why instead of using transmission gate, NMOS transistors are commonly used to realize pass transistor logic circuits. That means, in switch logic, whenever you realize Boolean functions using transistor as switch, usually an NMOS transistor is used as a switch instead of using transmission gate, although transmission gate is closer to an ideal switch. Okay. With this brief introduction, let us now see in what way how we can realize pass transistor logic circuits. First, let us discuss about some logic design rules. As we know, so whenever you are using NMOS transistor as a switch, then if we apply VDD here, let us assume the transistor is on. So, if we apply VDD here, the maximum voltage that you can use here VDD is VDD minus VTN. Suppose VDD is equal to 5 volt and VTN is equal to say 0.2 VDD, let us assume it is 1 volt. Then what will happen, if this is equal to 5 volt, here you will get 4 volt. Now, if this is used as a control signal to another stage, what will happen here? If we apply VDD is equal to 5 volt, here we shall get VDD, we shall get 3 volt. The reason is, you see here we are applying 4 volt. So, that means this transistor will turn off when this voltage will charge to 3 volt level. In a similar way, suppose this we apply as a control signal to another stage, then what will happen, and a VDD will get degraded too much, and here we shall get 3 volt. That means, if the output of a pass transistor logic, I mean NMOS transistor logic is switch, if it is applied as a input to a gate to the next stage, then the voltage further degrades. That means, so here it will be 2 volt, sorry. So, 4, 3 and 2. So, 2 volt. So, it is getting degraded, because if it is 3 volt here, this voltage, this point cannot charge beyond 2 volt. So, we can see there is severe degradation, and it may so happen that the next stage may not treat this. So, if we apply it to some gate logic circuit, then it may not be treated as a high level. Moreover, if it is driving to, say, suppose if it is driving to an inverter, then what will happen, the drive that it will provide to this NMOS transistor will be quite low, and as a consequence the because the drive, even if it is treated as a high level, the drive to this transistor will be quite low when the input is high, and as a consequence this will affect the switching characteristic of the device. That means, with 2 volt as the input voltage to the gate, as you know, the saturation current is equal to VDD minus VTN square, proportional to that, and as a consequence the current will be significantly less, and as a consequence the switching characteristic will be very inferior. So, from this we can say that one first design rule that you should use is one must not drive. So, this is the design rule, one must not drive the output of a pass transistor one must not drive the output of a pass transistor as input, rather control input, we should say control input to the next stage. That means, what we shall do, we shall never use this. That means, this signal we shall never use at control signal to the next stage. So, either we shall put an inverter here, buffer to restore the level, and then we shall apply to the next stage. So, we can, this is the first rule that you have to follow while realizing circuits using NMOS as switch. Okay. This is the first rule that you have to follow. Then the second rule we shall come from this observation. Suppose we have to realize a function f is equal to a plus b square c. Conventionally, if we realize it by a relay logic, the representation is like this. This is controlled by A, and this is controlled by B dash, and this is controlled by another switch C, and we get the output from here. That means, if we apply an input here and through these two switches, that means when A is 1, this switch is closed. So, signal will pass through it, and when B dash is equal to 1 and C is equal to 1, the signal will pass through it, and this is how it will work. And this is the circuit, this is the realization to realize this function f for of course, here you will apply VDD, or I mean in terms of our MOS circuits. So, that means, if we apply here VDD and then use these 3 switches, and we shall realize this function f. So, as we can see, whenever the switches are off, we shall be getting 0 volt, either A is either B is off or C is off, or A, B dash and C dash all are 1. In that case all are 0, in that case also the switch will be off. That means, if there is no path, then output will be 0. So, this is how you can realize by using relay logic. Now, suppose we use the same approach to realize the function by using pass transistor. Let us assume we use 3 NMOS transistors, 3 NMOS transistors. Here we apply A, here we apply B dash, here we apply C, and following the convention of relay logic, here we apply VDD, and here we are expecting the output V out. Question is, will V out be equal to what will be V out? Will it be equal to f? That is the question. Will it be equal to f, the function that is shown here? What is the answer? Unfortunately, if we realize the function based on relay logic, it will not produce correct output. Why it will not produce correct output? The reason for that is, you see, it will produce correct output so far as the high output level is concerned. That means, whenever this switch is closed, it will produce V out. Of course, it will not produce V out, but V out minus VDD. As you, let us assume we shall take it as a high level, but let us assume the case whenever. So, that means, whenever the output is say A, B, C. So, when the input is 1 0 0, then it will produce 1, or whenever it will the output is say 0 0 1, then it will produce 1, 0 0 1, B dash is equal to, so this path is closed, it will produce 1. That means, this is 1, this is 1, then also it will produce 1. But what about the case, say whenever we apply say 0 0 0, all are 0, or let us assume whenever the input say 0 1 0, I am not writing all possible combinations. So, for these inputs it is supposed to produce 0. Let us assume after applying any one of these inputs we apply 0 0 0, then what will happen? Shall we get 0 at the output? The answer is no. Why? The reason for that is, now whenever after applying any one of the inputs, whenever we apply either 0 0 0 or 0 1 0, what will happen? There is no path to VDD. Yes, this is off, this is off, this is whenever it is 0 0 0, neither this path nor this path is closed. So, you are supposed to get a 0 here, but unfortunately capacitor is now charged to VDD because of the previous input. So, as you know, it retains the charge at the output, and as a consequence it will continue to produce high if this input is applied after this, or this input is applied after any one of these two inputs. That means, after producing output, producing high at the output, if any input combination is applied for which we are supposed to get 0, it will not produce 0. In that case, what is the solution? Solution is that we have to realize the circuit in such a way that it will provide path for 0 also. That means, for 1 it is getting path through this, that means, to charge this capacitor to high level, the path is this, when A is 1, this is the path, when B dash C is 1, this is the path. But what about when F is supposed to be 0? So, we have to provide a path for discharging the capacitor. How can you provide that? That means, we have to realize, we have to put additional path such that the output is it should produce 0 when by discharging the capacitor when the input combination is such, output is 0. So, what we can do, we can provide this kind of thing, say A dash is connected and we provide 0 here, 0 means 0 volt. Now, as you can see, if we apply any other input combinations, then you will see that it will provide, it will for this input or this input, it will produce a 0 output, because this switch will now close and discharge the capacitor to 0 level. That means, so what is the design rule 2? What is our design rule 2? Design rule 2 is, it is essential to provide both charging and discharging path for the load capacitance. That means, when the output is supposed to be 0, there should be a discharge path of the capacitor. When the output is supposed to be 1, there will be charging path. So, this is how we have to use realize the circuit by using pass transistor logic. So, this is the second rule that we have to follow while realizing circuits by using pass transistor logic. What about the third rule? Is there any other problem here? Actually, another rule is there, design rule 3. Design rule 3 comes from, say, suppose this is a pass transistor network, pass transistor network, where you will be applying 0 volt and VDD as input, and of course, those various inputs you will apply as control signals, and here it will produce output, where let us assume we have a load capacitance CL. Now, it may so happen that the output there is a path directly to the 0 to this 0 volt, and also there is a path directly to the VDD. That means, both paths are realized advertently or inadvertently. It may so happen, because of some mistake in the design, what has happened, there is path both from 0 from the low level as well as from high level. This will lead to an output which is undefined. That means, it will depend on the that it will act, they will act as a kind of potential divider, and you will get a output which is neither 0 nor 1. So, you will get some undefined output. So, what is your design rule 2? So, you have to avoid simultaneous path to 0 and VDD. How? Later on we shall see. So, this is your design rule to be followed, and if we realize circuits by using 3 design rules, then it will produce correct output, and you can realize any general Boolean function. Later on we shall discuss in detail how we can realize general Boolean function using pass transistor logic. But before that, let us look at the advantages and disadvantages. First advantage is ratioless. Why it is ratioless? It is ratioless because the output is not dependent on the size of the NMOS or PMOS transistors. So, unlike your gate logic realized by using NMOS circuit or pseudo NMOS circuit, where the W by L ratio of the pull up to pull down device affects the output voltage at low level, and we have to maintain some ratio such that you get proper low level output. Here of course, that is not true, that means it is ratioless. What is the impact of this? The impact is, you can realize circuits with transistors of minimum dimension. That means 2 lambda by 2 lambda, lambda is the minimum feature size for a particular process technology. You can realize circuits by using transistors of minimum dimension, that means 2 lambda by 2 lambda, both for NMOS and PMOS transistors if you require. So, in this case however, you are realizing using only NMOS transistors. So, all of them will be of smallest dimension, smallest dimension means 2 lambda by 2 lambda, and obviously it will have a smaller area. This will lead to smaller area of realization. This is the outcome of this. Second is lower area due to smaller number of transistors. There is another important feature of fast transistor logic circuit is that you can realize Boolean functions with smaller number of transistors. Transistors are of smaller size and also you will require smaller number of transistors. Later on we shall discuss about the realization of some benchmark circuit, say full adder or other things. You will see the fast transistor logic realization will require smaller number of transistors, and as a consequence area required will be small. So, lower area due to smaller number of transistors, then lesser power dissipation. There is no static power dissipation and short circuit power dissipation. As we have seen here, although we are having path to 0 volt, path to VDD, but as you know only one of the two paths will be closed. That means, either there will be path to 0 or there will be path to VDD. There will be no path to the output simultaneously to 0 volt, 0 and VDD. As a result, it will never form never lead to short circuit power dissipation. We know that short circuit power dissipation occurs because there is a path from VDD to ground, but here that kind of path will never be established. Of course, if we follow design rule 3, that means, if we follow design rule 3 only then this will happen. If we do not follow it, then this problem may arise, but you have to follow design rule 3 whenever you are realizing circuits using fast transistor logic. So, these are the advantages, and obviously, you will be tempted to realize digital circuits or realize Boolean functions by using fast transistor logic. But before we venture to do that, let us have a look at the disadvantages. First disadvantage is higher delay in long chain of fast transistors. This is the first disadvantage. You see, whenever you apply a number of transistors in series, say you will be applying, let us assume VDD, and you will be realizing say there may be large number of inputs. So, let us assume here you apply B, C, D and so on. So, this is your input and this is your output V out. That means, whenever the signal is passing through a large number of fast transistors, what is the outcome of this? When the signal is passing through a large number of fast transistors, it will lead to long delay, because each transistor is associated with a resistance and a capacitance. We can model this as a somewhat like this, a resistance and a capacitance and a resistance and a capacitance and a resistance and a capacitance. Capacitance is connected to ground, this is connected to ground. If we have n transistors in series, we shall have n R and C, and this is connected to your load resistance. So, you are applying say input here, and it is passing through n number of resistors and capacitor to the output. This is your CL. What is the consequence of this? This will lead to large delay. So, how do you estimate the delay? whenever the signal is passing through a large number of transistors. This can be modeled as a single equivalent to as if you have got one resistance and one capacitance. So, this network can be modeled as this part can be modeled as a single resistance and a single capacitance, where the resistance value is equal to N into say R pass. This is the resistance of the pass transistor, and this is C is equal to I mean N into C, N C equivalent capacitance. So, equivalent capacitance as if N C and equivalent resistance is N R pass. So, what is the time constant tau? Time constant tau in this particular case is equal to N into R pass into N into C. That means, this is equal to N square R pass into C. So, whenever we follow this simple model, we find that delay is proportional to N square, and obviously, for 4 input delay will be 16 times that of the that of a single transistor, or when there are 8 transistors in cascade, delay will be 64 times. Obviously, it will be very large. However, it has been found that it is not so high, because this model that we have used is a kind of pessimistic model and not a correct model. A more accurate model can be used, more accurate model based on what is known as Elmore delay model. Elmore delay model. If we use this Elmore delay model, this can be modeled as if this time constant tau will be equal to effective, you can say, is equal to, this is say R1, this is R2, R3. In this way, let us assume there are n transistors, and similarly let us assume this is C1, this is C2, this is C3. Later on we shall assume that they are all same. So, then this delay, then the time constant will be equal to R1 into C1 plus these two resistances are in series to which is charging or discharging gas capacitor. So, R1 plus R2 into C2 plus, in this way we can say R1 plus R2 in this way Rn into Cn. If we assume that all R and N all are same, then this becomes equal to this will become equal to N into N minus 1 by 2 into R into C. This can be, if all C are same, which is equal to C, and all R are same R, then the value will be like this. That means, R C into N minus 1 by 2. So, this will be the time constant. So, the time delay based on this model will be equal to 0.69 n into n plus 1 by 2, it will be n into n plus 1, I believe, plus 1 by 2 into R into C. So, this will be the time constant. So, even with this value, let us assume the value of n is equal to 4. So, when the value is equal to n is equal to 4, this is 4 into 5 by 2, that means it is 4 into 5 by 2, that means value is 10, that means it will be 10 into 0.69. So, roughly 7 RC. So, it may not be 16, but 7 RC, that means when the number of n value of n is equal to 4, instead of 16 RC it is becoming 7 RC. So, in this way we find that the delay is increasing, may not be at the rate of square following square law, but it is definitely increasing at a high rate. So, what we have to do to overcome this problem? To overcome this problem, the solution is you will insert buffers you will insert buffers in between the pass transistors. Let us assume we use buffers at regular interval, maybe after few pass transistors, say buffer is inserted, then again you have got few such pass transistors. Here we have assumed that buffer is inserted after 3 transistors. So, whenever we do this and if the delay of these buffers is not very large, then the overall delay can be reduced. It has been estimated following that Elber model, this delay will be equal to 0.69 n by k, where you have got n pass transistors and delay it is introduced after k stages, CL into R pass into k into k plus 1 by 2 plus n by k minus 1. I am not deriving this, but this is the delay of the buffer. This is the expression that you will get. If you solve it, you will get 0.69, this will be equal to CL R pass. So, this k will cancel out into n into k plus 1 by 2, and this part will remain same, n minus k minus 1 into T buffer. How do you minimize this? To minimize this delay, as we know, the simple way of doing it, differentiate it and make it equal to 0. So, we can what you can do to minimize the value of this delay, we can have delta T p k by delta k. That means, after how many stages, k is the number of stages, after how many stages you will insert a buffer. We have shown non-inverting buffer here. So, if we put non-inverting buffer and to get the value of k, we shall differentiate it and then equate it to 0, and it has been found that k optimal value that you can get will be equal to 1.7, again I am not deriving it, T buffer by R pass into CL. So, this is the optimal value of delay, I mean the optimal number of stages that will produce minimum delay, and it has been by putting realistic values of R pass, CL and delays of buffer, it has been found that the value of k optimal is 3 or 4. That means, if we insert buffers at the interval of 3 or 4 pass transistors, then the delay will be minimized. So, this is how the impact of long delay of pass transistors can be minimized. Obviously, you cannot nullify it completely, there is no way of doing this, but you can minimize it by using this. So, whenever you are realizing circuits by using pass transistor logic, you will see that after 4 or 5 stages a buffer is inserted and buffer will not reduce the delay. Okay. Now, what is the second disadvantage? Second disadvantage is multi-threshold voltage drop. Multi-threshold voltage drop, that problem we have already discussed. Here as you see the transistor, here we are getting VDD minus VTN. Now, this voltage is not really good, in the sense that if we use it to drive an inverter, it will not be, it will lead to slow operation of the discharging. That means, if this capacitor will be discharged slower rate, because instead of 5 volt we are driving with 4 volt. So, how this problem can be overcome? Because normally you will see you will be combining pass transistor logic with static CMOS. You may have to put inverters, static CMOS inverters along with pass transistor logic. So, in such a case you will face problem. So, this multi threshold voltage drop, particularly if we use say 2 pass transistors in series and there this one is used as an input to a next stage, then problem will be more severe. How we can overcome this problem? This problem can be overcome by using what is known as swing restoration logic. Swing restoration So, you have to provide a swing restoration logic after whenever you take the output to the next stage. What is the role of the swing restoration logic? It will raise the voltage level to particularly the high level to VDD. So, how it can be done? Normally say suppose this is a pass transistor logic and this is going to an output. So, what will you do? What you can do? You can put a weak PMOS transistor and ground it. So, if you do that, as you know, the voltage level will be pulled to VDD through this weak PMOS transistor, and this is one approach that can be followed. Another approach is in addition to this weak PMOS transistor, you can put an inverter along with a weak PMOS transistor. That means, this will be applied to an inverter then you will be having a weak PMOS transistor, this is connected here and this output will be coming from here. So, what will happen in this? Even this inverter will get high level voltage, this is VDD. So, this weak PMOS will pull the output to high VDD level. So, this is this kind of swing restoration logic either by using a single weak PMOS transistor or along with weak PMOS transistor along with an inverter can be used to restore the voltage level. Here at this point we can see we have raised the level. So, this will serve as not only swing restoration logic. So, swing restoration logic along with inverting buffer. So, this will act as a buffer. So, this can be applied to the next stage. So, you see this type of thing you have to do when realizing circuits, realistic circuits by using pass transistor logic. So, this is the second problem that we shall face. Third problem is sneak path. Sneak path I have already mentioned about it. Sneak path occurs when because of the problem of logic design, there is path to VDD and ground. As you can see here, say here you are supposed to get F, but what has happened simultaneously for some input combination, in this particular case A is equal to 1, B is equal to 1, C is equal to 1, D is equal to 1, you can see there is a path from 1 to 0. So, you can see here the voltage will be neither high nor low, something in between, and not only that there will be that kind of it will lead to short circuit power dissipation. So, this so you have to design such that there should not be any sneak path, which I have already mentioned as the third rule. So, you have to design in such a way so that there is no sneak path. How can it be avoided? So, how can we avoid sneak path? Sneak path can be avoided by using multiplexer based circuit design. So, use multiplexer based system design. What is a multiplexer? Multiplexers, as you know, it has got multiple input and a single output. You can multiplex the inputs. So, suppose you have got you are familiar with say 2 input multiplexer. So, here there are 2 inputs and there is a control input and you produce a output. So, this is the control signal and these are the two inputs that we apply. This is known as 2 to 1 mux. So, in a similar way you can have 4 to 1 mux, say 4 to 1 multiplexer. In this case you will be having 4 inputs and there will be a single output, and of course, you will require 2 signals to control which input will be selected to be connected to the output. So, essentially the role of this control signal is to control the path to one of the 2 inputs in this case, and here to one of the paths, one of the 4 paths in this particular case. How can you realize this multiplexer? You can realize multiplexer by using switch logic, using pass transistors. For example, this particular 2 to 1 multiplexer can be realized in this way. So, this is a 2 to 1 mux. Here is one input, first input, here is second input. What you do here? You apply A here, and in this case apply the control signal A bar. So, control signal A bar is here and control signal A is here. That means, your control signal is A, this is 1, this is 2, and here you are getting output V out. So, that means, when A is equal to 1, the 1 input is connected to the output. When A is equal to 0, then the input 2 is connected to the output. This is how you can realize a Boolean function. I mean, you can a multiplexer is realized. In a similar way, a 4 to 1 multiplexer can be realized in this manner. Here you will require 2 pass transistors in each path, of course, and there will be 4 paths. There will be 4 paths. So, all the 4 paths are tied together, and here it produces V out, and 1, 2, 1, 2, 3, 4, and let us assume these are A and B. So, what you will do, this will be A B, and this is A B bar, A bar B, and A bar B bar. So, what will happen when both the inputs are 0, then I mean both the inputs are 1, path 1 will be connected. When A is 1, B is 0, then this path will be connected, path 2 will be connected. When A is 0, B is 1, then path 3 will be connected to the output. When both are 0, then path 4 will be connected to the output. Question is, how this multiplexer can be used to realize Boolean functions? It can be very easily done from the truth table. For example, say a function f can be, let us assume it is a function of 2 variables, can be always expressed as in terms of say g1 f say 00 sorry g0 f00 plus g1 f01 plus g3 f10 and plus g4 f11. That means, suppose A and B, these are the 2 inputs, and 0 0 0 1 1 0 1 1. Then depending on whatever is the say this is f, say let us assume we are realizing 1 0 1 0. Then G0, G1, G3, G4 can be directly taken from the truth table. That means, F0 the G0 value of G0 is equal to 1, value of G1 is equal to 0, value of G2 is equal to 1, value of G4 is G3 is equal to 0. That means, what will you do if this is the multiplexer? You will apply A and B as control input, and you will apply G0, G1, G2 and G3, which are essentially Boolean function, I mean Boolean variables. You can see depending on the function you are realizing, they will be having 0 or 1. So, accordingly we will apply, and this will realize f. So, it can be proved that a multiplexer, 4 input multiplexer multiplexer can realize any function of two variables. Not only, I mean, later on I shall prove also, instead of applying 0 and 1 here, if you can apply one variable here also, instead of, say, suppose there is another variable c. What you can do, you can apply 0, 1 or c and c dash. If you are allowed to do that, that means a 4 input mux can realize any function of 3 variables. You can expand around a and b, then these functions g 0, g 1, g 2, g 3, these are known as reduced functions. Reduced functions. These reduced functions you can find out, those reduced functions will be either constant, that means 0 or 1, or function of the third variable c, that means either c or c dash. So, those you can apply 0, 1, c and c dash, and you can realize any function. That means, using past transistor logic you can realize Boolean function using multiplexer as the kind of building block, where multiplexer is realized using past transistors. So, this is how it can be done, and it can be proved that this is free from all the problems that I discussed. That means, all the design rules which I have mentioned is followed here. None of the 3 design rules that I have told is violated in this case. So, you can realize functions in this way, and that is the reason why multiplexers are known as they can, since they can realize any function, they are considered as universal logic gate. So, since they can realize any function. So, in fact, later on if you study FPGA, field programmable gate array, there are multiplexer based field programmable gate array by Actel. There multiplexer is used as building block of digital circuits. So, how multiplexer is realized, that is no concern there, but any Boolean function can be expressed in terms of multiplexers, and this is how it can be done. So, we find that this is a technique by which you can realize Boolean functions and using multiplexer as building block. Okay. Let me consider another very important disadvantage, complementary control signals. We have already seen that in some cases you have to apply control signals in the complemented form. If we consider the network, multiplexer, within the multiplexer network we can see B bar, A bar, these are also present. That means, you have to apply both the variable, control variable and its complement to control the past transistor logic network. That means, this is a disadvantage, you have to, you have to generate the control signal. In other words, you have to use what is known as dual rail logic. Dual rail logic. So, you will generate F as well as F bar, so that F and F bar can be used as control signal to the next stage. So, these are the main drawbacks and advantages that we have discussed. Now, we can summarize what we have discussed in today's lecture. I have discussed about introduced the basic concept of past transistor logic, discussed about the logic design rules, discussed about their advantages and disadvantages, and discussed techniques how to overcome these problems. In my next lecture, I shall discuss about how you can realize complicated Boolean functions using past transistor logic, that means systematic technique for logic design, and also there are some logic families, past transistor logic families which have been proposed in the last couple of years. So, I shall introduce the past transistor logic family to you. Thank you.